This is the third video associated with Lecture 8, and this video focuses on accessing spatial data in R, so geometric data that can be used for mapping. We're going to talk about accessing three types of data: data on states and counties, data on census geography, so census tracts, block groups, and blocks, and then other features that are available through the package we'll be focusing on, tigris. Tigris is a reference to the Census Tiger database, which is the Census Bureau's repository for all of their geometric data that they make publicly available. To begin, I want to talk about downloading data on states and counties. This is a common level at which we make maps in the United States. And Tigris has functions for accessing both state and county data easily from within R. I want to talk about accessing states data first. What's great about Tigris is that all of the functions are named after the type of geography that you're downloading. So for example, the states data is downloaded using the function states. All of the functions share a common set of parameters and arguments, which makes working with them easy. The states data has two that we'll focus on today. One is CB, and the CB argument for all of the functions in Tigris is a determination about whether the data should be generalized or not. The most accurate spatial data, which by accuracy I mean geometric data that has the most close relationship with the quote-unquote true shape of different features, can be obtained if we set CB to false. If it's set to true, we'll get generalized data that has slight deviations from that most accurate level of detail. When we're mapping at the country, national level, all US states, and even at the state level, it sometimes is easier to use generalized data because there's less small changes in each of the features' boundaries that can be hard to visualize at such a small scale. If we set CB to true, we have three options for resolution. These correspond to the three resolutions that you can look back at Lecture 3 to get a sense of how scale and representation change in Census Bureau data. The example I have here is downloading US states that are generalized to the most detailed version of the generalized data, which is the 1 to 500,000 scale. Remember, we only need to specify the resolution if CB is true. We have a separate notebook for this part of Lecture 8, and at the top of the notebook, we have all the dependencies we need for this part of the lecture. We have ggplot for previewing maps of these data, dplyr for doing some very simple data cleaning, the SF package, which will need to convert Tigris's output to SF objects, and then finally, Tigris itself. We'll go ahead and execute that code chunk and take a look at the states function. This replicates the syntax that was available on the slide. And so if we execute it, our generalized states data will be downloaded to R. One trick with working with Tigris is the data are downloaded as SP objects. SP objects are an older data frame format for storing spatial data that are beginning to be replaced by the package we've been using, SF. SF includes a function, st_as_sf, that allows us to quickly convert SP objects into the more modern SF objects. It only takes one parameter, the name of the SP data that we want to convert. And so for example, if we've downloaded our states data, as you see here, and saved it to an object called states, we can then run that object through the st_as_sf function and convert the SP object to SF. You can tell that you're working with an SP object by looking up in the global environment. You see here that the states data frame has the text large spatial polygons data frame next to it in the environment tab. This is a giveaway that you have SP data. In the next code chunk, we have a pipe that accomplishes two things. First, we pass the state's object through st as sf. And if you're using it within a pipeline, you do not need to include an additional argument inside the parentheses. Once we've converted it to sf, we can use all of our dplyr verbs on it. And so here we'll filter out all of the data so that we only have Missouri left in the object. And we'll assign the result of that to an object called mo. When we execute the code chunk, we can open up the object in our global environment, and we can see just that one row for the state of Missouri. Once it's in our global environment, we can use geom_sf to plot the data just as we have from making maps at other points during the semester. Downloading county data is largely the same. The tigris function for accessing county level data is called counties. Like the states function, it takes an argument called CB and an argument called resolution. These work the exact same way as they do in the states function. The additional piece is that we now need to specify a single state we are downloading data for. This can be specified either using the name of the state, like Missouri, its USPS abbreviation, MO, or the numeric FIPS code value for the state, which in Missouri's case is 29. And here we have an example of what that would look like. We take the state of Missouri's counties and download them generalized to the highest possible degree, 1 to 2 million scale, and save it in an object called mo counties. Our sample notebook for the lecture contains this same exact function. We have the state of Missouri. We're downloading generalized data to 1 to 20 million scale and saving it to an object called mo counties. When we execute that code chunk, depending on the degree of generalization and the size of the state you're working with, it may take a little bit to download, but it will be saved as an SP object. So we need to use st as sf to convert it to an sf object, and that's what the code chunk beginning on line 55 does. So we'll execute that, and now we have data that looks just like the tables we are used to working with. One row for every county in the state of Missouri. Finally, because we have an SF object, we can plot these using geom as SF. And here we have a generalized map of Missouri's counties. Tigris can also be used to download geometric data for census geography. Census tracts, census block groups, and census blocks. The functions to download these varying levels of geography all work the same way. They're named after the geography you're downloading, and they take the same types of arguments. So here, for example, we have the tracts function. We need to specify the state we are downloading data from, the county we're downloading data for, and whether we want it generalized or not. If we want it generalized, we should also provide the resolution we would like it at. The county can be either the name of the county or its 3-digit FIPS code. Here's an example, downloading tract level data for the city of St. Louis. Here I've just provided FIPS codes for both the state and the county, but again, you could provide strings that describe those accurately as well. I don't generally generalize the sub-county spatial data. I download it at the most accurate level of representation available. Here I have the same code in our notebook, so downloading the city of St. Louis's census tracts into an object called STL tracts. Once it's downloaded, we can convert it to an SF object and plot it. And there we have a map of the 106 census tracts within the city of St. Louis. We can do the same for census block groups and also census blocks. Finally, I want to point out that Tigris has a number of other functions for downloading and working with spatial data available through the Census Bureau's Tiger database. It's possible to directly download into R data about bodies of water, both polygon and line data, as well as data about the United States as a whole, the U.S. boundary, coastline, and congressional districts. There's also landmark data, data about Native American reservations and trust areas, and also data about infrastructure, roads and railways, state legislative districts, and urban areas. These are just some of the functions available in Tigris. There are even more. You can check out Tigris's documentation through CRAN to get a complete list of the features that are accessible.